Okay, so here we will talk about the electric field due to a line of charge. Okay, so this part will the difficulty maybe becomes higher than the previous case, but yeah, you will also feel like, oh, we start to use the integration, but you may consider it still, but because it's just like integrating a constant, so it's just like multiplication. Why you just use multiplication, then it's all done. The reason is that I'll try to use the integration to let you familiar with how we can use calculus to solve physics problem. So later on, if it is not a constant, then yeah, you still know how we can use calculus to consider some complicated problem. Okay, so first of all, here we talk about the electric field due to a line of charge. Line of charge in other meaning is like a charge ring. Charge ring. Okay, so it says the equation for the E field set up by a particle does not apply to an extended object with charge, which means has a continuous charge distribution. Just like in the previous chapter, if we only have two charge of particle, then we can calculate the force. If using the Coulomb's law, I mean, if we have a continuous distribution of a charge, then calculating the total force will need some calculus, need some integration. So was this case. So if we only have a single charge particle, then if we need to calculate the E field, then you just plug in the E equals K times Q over R squared. And if we have discrete charges to generate the E field, then you can only calculate the E field one by one and then finally add them together with the vector sum. But if it is a continuous charge distribution, then we cannot just add, and actually it is still add, but we need to add infinite amount of terms. So it becomes an integration from addition to integration. So that's why we need to use the calculus. Okay, so here if we need to find the electric field of an extended object at a point, we first consider the electric field set up by a charge element dq, which means that yeah, actually it is a continuous distribution, but we try to for this case it is a charge ring. So here we try to cut this ring into many small segments. So every small segment will look like a charged particle, although it's not. But if if we try to cut it into infinitely small enough, infinitely small, then it turns out to be a charged particle. Of course, this ds look like quite long, but yeah, it just show you with greatly exaggeration for clarity. Otherwise, if it's drawing too small, then you don't know, oh, this is ds. So, but actually, what we really do is try to cut it into very small enough segment, so that for every segment, we can consider that to be a discrete charge. But if we cut it into infinite small segment, then there will be infinitely large amount of discrete charge. So we need the Riemann sum. Riemann sum, just as what you learned in the calculus class. So a Riemann sum turns out to be the integration. So we try to add them together, adding infinite amount of terms. So it becomes an integration. Okay, so this element set up the E field dE at point P. So for this part this part ds this part ds, it will have a charge amount dq there. So this dq we can consider it as a discrete charge. It will generate the E field dE at point P we concern. Okay, so the next part is, so for this course we generally consider some symmetrical structure. Symmetrical structure 对称的 so that it is more possible for hand calculation. And in that case, for symmetrical structure, generally we can find something cancelable, which means that for this one, this is a perfect circle, and then this axis go through the center of this ring, and that is perpendicular to it. So similar to the dipole, we can only calculate the E field generated by this structure on this z-axis. Okay, so this is a perfect circle, and then a point on this z-axis, we can easily find a symmetrical point. So which means that this is the center of the circle, and then this is ds. So we can just draw a line, draw the diameter. Okay, so this part we may call it ds or ds prime, whatever you want to call it. So this ds prime will also have a dq prime there, and then it will generate the E field at point P, somehow pointing to that side. Also, this is dE, this is also dE. Okay, so as much as the ring has a uniform distributed, I'm not sure whether it mentioned it there. Yeah, here a ring of a uniform positive charge, 均匀的正电荷. Okay, it can also be negative charge, so the E field point to the opposite side. Okay, so as much as this is uniform, so if this ds and this ds prime has the same length, so the dq and dq prime will be the same amount, which means that this dE and this dE should have the same magnitude, although they point to a different direction. Okay, and then here we try to consider the cross section go through this z-axis. So on the bottom left corner, you can see this figure. Okay, so this dE is generated by ds, and this dE is generated by ds prime. This is from ds prime. This is from ds. Okay, so they should have the same magnitude, although they point to a different direction. And as much as they are the symmetrical to the center of the circle, which means that okay, in this plane, okay, so all the horizontal component will cancel each other. So this one and this one will cancel each other perfectly because they are symmetric. If you just choose or maybe this ds and some ds prime there, this is not symmetric, so they cannot perfectly cancel the horizontal component. But as much as for a circle, you can always find the symmetrical part. So the horizontal component can be perfectly cancelled. If you have this part, then the symmetrical part is there. So the horizontal part, you can always find a pair of discrete charge, so that they perfectly cancel the horizontal component. But of course, the vertical component cannot cancel each other, because for the horizontal component of these two vectors, they point to the same direction. But at least we only need to consider the horizontal component rather than the horizontal component. The horizontal component must be 0 at this axis. Okay, so finally, we only need to consider the vertical component as at point C to be dE times cosine of theta. The theta is this angle. So theta is this angle. So the c-axis component should be dE cosine of theta, because this is the adjacent side. This is theta. Okay, so here after the cancellation, we know that we only need to deal with the vertical component. So the next is to add all the vertical component throughout the whole ring. Okay, so the next step is to adding the components. So the parallel component each have magnitude dE cosine theta. Okay, so of course we need to do the integration. We need to substitute to some known variable. What is known as the known variable is that this z is a known variable. Because we consider the distance from the center point to the desired point. R might not be the known variable, but capital R can be a known variable. Capital R and Z, they are known variable. So we try to express this thing into the known value. So first of all, cosine of theta. This is R, this is Z. So cosine theta is Z over R. R is not a known value, so we may try to express it as Z and capital R. So according to Pythagorean theorem, so we have R to be square root of Z squared plus R squared, like this. So this is due to the Pythagorean theorem. Okay, or we can just write the square root to be 1/2 power. Okay, so this is cosine of theta, and of course the whole thing is dE cosine theta. So dE cosine theta. Okay, dE dE. So this part ds should have the charge dq, and actually we would like to integrate over the ring with variable ds. So and here we will know ds and dq should have some relationship, and actually total amount of charge is q. We should have this is the total amount of charge q. So q should be the length of this ring should be the diameter of the circle, will be 2 pi r, and then times lambda will be the so-called this one, the linear charge density, because it is a ring, so this is in 1D. So lambda is the linear charge density. So this has a unit of meter. This is coulomb. So lambda should have the SI unit of coulomb per meter. Okay, so this is the definition of the linear charge density. And here, the relationship between dq and ds should also be dq equals lambda times ds. So this is the length, this is the charge density. So if we just multiply them together, it will become the charge. Okay, so which means that dq will be lambda ds. Okay, so which means that dE should be k, which is 1 over 4 pi epsilon naught, times dq over this distance. The distance is from here. The distance should be from ds to the point P, which is small r. So this is small r. And similarly, r is not a known variable. So we need to express it as a known variable. So this becomes k times dq is lambda ds, and then so ds can be integral, because we need to integrate over the ring. Okay, so if we write it as dq, we have no means to integrate it. And then r is similarly, using the Pythagorean theorem, it is r square. I mean, as r square, it should be c squared plus capital R squared. So we all together. So here we have this expression multiplied by this one. This one is the cosine of theta. Cosine of theta. So here, 1/4 pi epsilon is put here, and then we have a c to be here, and then we have lambda to be here, and then finally we have a ds to be here, and then also this is r squared, and this is also r to the square root of r. So altogether we have small r to the 3/2 power. So this is small r is c squared plus capital R squared to the 3/2 power. So this is the expression of dE cosine theta. So we find the vertical component generated by ds. I mean the vertical component of the dE of the E field generated by ds. So this is the small part, and finally we add all of them together to find the total E field generated by the charge ring. Okay, so the last part is the integration. We try to add all of them together. So the total E will be the integral of L dE cosine theta. Okay, dE has the expression of this one, so we just put it here. Okay, so the integration variable ds is this ring, so it starts from 0 to 2 pi r, so nothing special. Okay, so this is ds, and all the other variables are not related to ds, which means that we are actually integrating a constant. Integrating a constant is easy because it's just like this constant multiplied by the difference between the lower and upper bound, or upper and lower bound. So finally, it becomes this one. This box, this green box, go to here, and then the circle one goes to here. Okay, and then here we can do some cancellation and simplification. Just now I already mentioned that Q equals 2 pi capital R times lambda. So we can do some cancellation. We can do some simplification, which means that here we have lambda, we have 2 pi R. So it turns out to be Q. And then for the other thing, we have a Z to be here. And then we have 1/4 pi epsilon naught to be here. And then finally, we have this term to be here. Okay, so yeah. So this is the final expression. Charge ring to be this one. It looks a bit complicated, but similarly, we also apply the far field condition. Which means that Z is much larger than capital R. We consider the point P, which is a distance much larger than the radius of the ring. Okay, then it will follow a much more elegant expression. So here, if Z is much larger than capital R, which means that for this term, we can just ignore R squared. So this term becomes Z squared and then to the 3/2 power, which becomes, so this term will become C cube. C cube and C will cancel. C cube and C will partially cancel. So it turns out to be C squared. So finally, we have C squared in the denominator. And then this expression is very good looking, very elegant. So it's just like all the charge are concentric at the center. So all the charge are concentric at the center, and then point P here. So the distance is Z. So when we try to consider the E field generated by this charge, so it's just like all the charge are concentric at the center, and then when you generate the E field here, you calculate as K times Q over C squared. So just as simple as this. So that's why we need the far field condition to further simplify this expression. If we don't have the far field condition, the expression will be looked as the same as this thing. Okay, it looks more complicated. But here, yeah, as much as we have the far field condition, it's just like as simple as this. We consider all the charge to be at the center. Okay, so next we have a sample problem. So we try to familiar with how to use the calculus to solve the problem. So here, rather than a whole circle, we only have an arc. Okay, so it says a plastic wad have been having a uniform distributed charge negative Q, so it doesn't really matter whether it is plus or negative. Okay, so the rod has been bent in 120 degrees circular arc. Okay, so plus 60 degree, negative 60 degree from the x-axis. So replace coordinate axis such that the axis symmetry of the rod lies along the x-axis, and the origin is at the center. So this is the origin at the center of the rod. Of the curvature P of the rod. Okay, in terms of Q and R, what is the electric field E to the rod P? Okay, so let's try to do this here. So similarly, we'll try to cut this rod into many small segments, like this one, ds. And then as much as the x-axis is the symmetrical part, so we always can find the symmetrical part here as a ds prime. Okay, the charge is negative, which means that if this is ds, there will be a dq on it. dq will be a negative number. So dq lambda ds will be dq. So which means that for this ds, de will be point to the dq, which means point to the top right side. And for the symmetrical part ds prime, the de prime will point to the bottom right side. Okay, in that case, as much as the charge is uniform distributed, so de and de prime should have the same magnitude. Of course, they point to the different direction, but as much as ds and ds prime are symmetry to the x-axis, which means that the y-axis component of these two things, the y-axis component of these two things will perfectly cancel each other. So we only need to consider the x-axis component dex. Okay. Okay, so here we have a de equals k times dq over the radius. What is the radius? Radius is r, small r. Okay, the radius is small r. Okay, so this is small r squared. Small r is a known variable, so that we don't need to express it as other variable. Okay, so here dq should be lambda ds, so we can write it as k times lambda ds over r squared. Okay, so next, we consider the x-axis component because as we just discussed, the y-axis component dey will perfectly cancel each other, so we only need to consider dex. So dex will be de cosine of theta. Okay, this is theta starting from x-axis to the de. So this is the adjacent side. So that we use a cosine of theta. Okay, so in that case, de is this thing, k times lambda ds over r squared, and then cosine of theta. Okay, so here when we try to do the integration, we will integrate over the angle from, just say, a negative, this is negative 60 degree to positive 60 degree, or in radian. Usually for calculus you use gradient. 60 degree will be pi over 3, starting from negative pi over 3 to pi over 3. Okay, in that case, we will try to use d theta rather than ds. Okay, so we need to change this variable. So this is like a polar coordinate, 极坐标, polar coordinate. So for polar coordinate, you know that suppose this is the axis, and then this is a circular arc. This is a circular arc. This is so-called d theta. This is ds, and this is small r. So I think in high school mathematics, you know that ds should be r d theta. Okay, it should be the radius multiplied by the angle in radian, and it will be the length of the arc. Okay, so in that case, we will apply ds to be r d theta. So it becomes k times lambda r d theta over r squared, and then cosine of theta. So of course we can cancel this r with this r squared plus only. So next we can try to write it like k lambda over r, and then cosine theta d theta. Okay, so this is dex. Okay, then we can try to do the integration because all these variables are independent to theta. So this is the function related to d theta we would like to integrate. So finally, the total E field will be the integration of dex. So we can just plug in this expression, k lambda over r, and then cosine theta d theta. So the integration, the lower and upper bound of the integration will be negative pi over 3 to pi over 3, as I mentioned. Okay, so here we know that these are constant for the theta, which means that we can just put it outside, k lambda over r, and then we have an integration of a cosine of theta d theta from negative pi over 3 to pi over 3. Okay, so the antiderivative of the cosine theta is sine of theta. So we have a k lambda over r, and then we have a sine of theta evaluate from negative pi over 3 to pi over 3. Okay, so cosine, sine of pi over 3, sine of 60 degree is square root of 3 over 2, which means that this one subtracting this one will be square root of 3 k lambda over r. Okay, so, and of course, lambda is not a known variable. The known variable is only r and capital Q. So we need to substitute it back into Q. So of course Q will be the length times the lambda. So this is the length of the arc. The length of the arc will be, the angle is 430 degree, which means that this is two-third of pi, times the radius, small r. So this is the arc length of the whole rod. Okay, this is the radian times the radius. It will be the length of the arc. Okay, so we have this expression, capital Q to be 2/3 pi r times lambda. Or we can just slightly move over the term. We should have lambda to be 3Q over 2 pi r. Okay, and then we can just plug in this one here. So finally we will get 3 times square root of 3 KQ over 2 pi r squared, like this. Okay, so this is the closed form expression. This is the closed form expression of this problem. Okay, so yeah, just finish this off in the previous page. Okay, so next we have a checkpoint. So this figure here shows 3 non-conducting rods, 1 circular and 2 straight. Each has a uniform charge of magnitude Q along its top half and other along its bottom half. For each rod, what is the direction of the net electric field at the point P? So this checkpoint lets you familiar with how to do the cancellation. We don't need to do any mathematics, don't need to do any calculus. We just need to consider the cancellation. Yeah. Okay, so for the first one, this is this is plus Q, this is negative Q. And then here we would like to consider the direction of the net E field at point P. Point P is the center, at least for the first one, is center of the arc. Okay, so so let's consider the two part individually. So for the plus Q, we can consider, because this is altogether a 90 degree, so we will expect the E plus will point to the top right direction, with 45 degree with the x-axis. Okay, similarly for the negative Q, the E field generated by it will be pointing to it. Okay, so the E minus will be pointing to the top left, also with a 45 degree to the negative x-axis or the y-axis. Okay, so the overall E field for part A, okay, we can see the x-axis component will cancel each other, which means that this one will point to the plus y-axis, or pointing to the upward. Okay, so for the next one, so we can see the whole rod is a positive charge, plus Q for the bottom part and plus Q for the top part. Okay, so here actually for the top part, as much as this is a positive charge, so we will imagine this will point to this side. Yeah, somehow to the bottom right. Okay, so this is maybe we call this part 1, this is 2, so this is E1. We cannot know what is the angle here, because we really know how long it is and how long the distance from here to there. So we cannot know the exactly what the angle is there. But also for the part 2, yeah, we can see E2 should point to the top right direction. So actually these two angles will be the same thing, which means that the y-axis component will perfectly cancel. Finally, the E will point to the right side, or the plus x-axis, or point to the right side, Okay, for the part C, okay, this is 1, this is 2, so still E1 will be similar. And E2 will point to the negative charge, so it points to the bottom left. So this is E2. So altogether, E will point to the downward. So this is downward, or negative y-axis. It depends. Both have the same meaning. Okay. So next, we talk about another structure called the electric field due to a charge disk. Just now we have a charge ring. Okay, so here for the charge disk, of course we need to separate into many small segments. So there are different ways to cut it into small charges. So one trivial way is to cut it off. If we cut a circle according to the Cartesian coordinate， 迪卡的坐标或者是直角坐标系。Okay, so if we try to cut it like this, it will be much more difficult. When you try to learn how to calculate the area of a circle, so you probably need to integrate something like r squared minus x squared, and then take the square root, and then dx from negative r to positive r, and then multiply by 2. So this is the area of a circle, and then this is how you cut the circle vertically, so that this is more difficult more difficult to calculate, because you need to do some change of variable, like x equals to r times cosine of theta, something like that. You need to do some change of variable. And actually, change of variable means this is the polar coordinate. This is the Cartesian coordinate. So that's why for a circle, if we use a polar coordinate, will be easier. So that's why we'll try to cut this circle like this, with the polar coordinate, and also we try to cut it like this. Okay, so everyone, actually they are not rectangle, but if it is very small, then you can consider every small part is still a small charge. So of course, if we don't really use the result there, we actually need to use this method. We try to cut the circle with the polar coordinate. Like this. But as much as we already calculate the E field generated by a charge ring, then we don't really need to cut it over the angle. We just need to cut the circle like this. So a a charge disk is like many ring with different radius. So from 0 to capital R, then all the different ring with different radius form a solid disk. So we can make use of the result for the charge ring, and then we can simplify our calculation for the charge disk. Okay, so that's why we will make use of the expression for the charge disk. A charge ring. Charge ring. So this is for the charge ring. Charge ring. Okay, so but here we try to consider a ring to be a small part of charge. So here, rather than Q, we write it as dq, and then the dE will be written as dE. All the other remains the same. Another thing is that we use capital R to stand for the radius of the disk. So for the ring, we will consider this R to be small r. So we integrate something with the dr from 0 to capital R, and all things will settle. Okay, so next part. Okay, so this is what we get from the previous page. Okay, so we want to sum from R to be 0 to capital R, which means that we have an integration of something dr from 0 to capital R. Okay, so next we need to do some change of variable, because this is dq, not dr, so we need to do some change of variable. So first of all, dq can have a relationship with a dA. dA is the area of the ring. Okay, so although for the previous derivation we consider the ring to be very thin, but here we'll consider the ring with small thickness to be dr. dr will be the thickness of the ring. Okay, so here we will introduce another variable called sigma. Is the surface charge density. Just now it is the linear charge density lambda. So here we use another variable sigma to stand for the surface charge density. So of course this is a surface charge density, and if it is multiplied by the area, it will be the charge at that area. So this is dq over the whole ring, and then we have a sigma multiplied by dA will be the dq. Okay, so we change a bit. Although this is dA, this is dr. This is still not the same thing. So the next is what is dr in terms of dr. Which means that we try to consider what is the area of this ring. Okay, so this is a ring. You can calculate it perfectly, like you calculate the area of the larger circle and then subtract by the smaller circle. But actually here we don't need to do that. We can try to cut this ring out. After cutting this ring, and then we try to expand it to be a rectangle. Okay, whoa, it looks so hard to imagine, because it is a ring. After expanding it, it shouldn't be a rectangle. But yeah, as much as this is small enough, you can imagine this is a rectangle, and then the rectangle should have a height of dr, which is the thickness of the ring, and then the length of the ring, the width of the rectangle should be the diameter of the circle, which is 2 pi r. So the area A, the dA should be 2 pi r times dr. So we plug this one into here. So we will have 2 pi r dr multiplied by sigma, and then we can plug this one. This is DQ. We can plug it one back to here. Okay, so here we just plug it back to here. So we have a we have this one to be here, and then DQ is the whole thing. So we have a sigma 2 pi r dr, and then we have z to put here, and of course we still have this term putting here. Okay, so we can do some simplification. Okay, so let's see. We have 2 pi partially cancel with sorry. Okay, we have let's see, we have this pi and pi cancel each other, and nothing else. So we can see we have sigma c here, and then we have a 2 r dr, and then in the denominator we have 4 epsilon naught, and then we have this big term. Okay, so we have done some simplification. Okay, so this is dE, and then we can integrating dE from 0 to r. Yeah, because we already have dr here, so that we can integrate from 0 to capital R to form the total E at point P. Okay, one thing I forgot is that this is the surface charge integral. So the SI unit should be C over m meter square rather than C over m. C over m is for the linear charge density. For the surface charge density, the SI unit is different. Okay, so next, we can just plug in the expression of dE here so that we can do the integration. So the integration is like this. Okay, of course, this term is this term, which is independent to r, so that we can just put it out as a constant. Okay, the remaining stuff is 2r dr, and then also this part. So using some change of variable, or it is the reverse version of the chain rule. So we have of course we have a dr 2r dr to be dr square, and then plus c square is just a constant to the r. So yeah, we don't need to care. So it's just like, if you don't familiar with this written style, you can regard it as d r square plus c square over dr. So you take derivative of this expression to r, so it becomes 2r, and then you move this one to the right side, so it becomes 2r dr, and then the other side will be this one. Okay, so here we already get this one, which is exactly as this one. If you need to change a variable, you can change to another variable. Just say u to be r square plus c square, and then in the front it becomes something like u to the minus 3 over 2 du, something like that. But you need to change the lower and upper bound accordingly. So I think we don't need to do so. You just can see that this one and this one are the same. So it's like a polynomial, integration of a polynomial. So to the 3 over 2 power, which means that the antiderivative is this thing to negative 3 over 2 plus 1. So it becomes negative 1/2. And then also we need to divide this one. Okay, divide this one. So we have a negative 1 over 2 in the front, and then we evaluate from 0 to capital R. Okay, so so as much as here we have a negative sign, which means that we can evaluate it from at 0 and then subtract by this expression evaluated at capital R. So first of all, to cancel this negative sign, and also this negative 1/2 or this 1/2 can be putting in the front. So we have a 2 in the denominator here. And then we try to evaluate this expression with this is small r. Maybe this is too much. Okay, this is r equal to 0. R equals to capital R. So here we try to evaluate this one with small r equal to 0. So it becomes c squared. R becomes 0. And then take the square root because this is a negative 1/2 power. So it goes to the denominator. Okay, so this is 1 over square root of c squared, which is 1 over c. And then for the second term, we evaluate this one, r, to be capital R. And then take the negative 1/2 power. So negative minus 1 over square root of c squared plus r squared. Okay, so like this. And then we try to distribute this c into here and there. So this c and this square root of c squared will cancel each other. It becomes a 1. And then c goes to the numerator, so goes to here. So finally, this is the expression of the E field generated by a charged disk. Okay, it looks quite complicated, but here we will make an assumption. Okay, so at least we know this is the expression of the E field generated by a charged disk. Okay, so here we make an assumption is that this R is infinitely large, which means that this disk is very large. If this is very, very large, infinitely large, you may ask, oh, how come a disk can be infinitely large? But this is just an assumption. If R is infinitely large, then you can imagine this term will shrink to 0. This term will shrink to 0. Why? Maybe you are not familiar. So let's try to do something like we try to divide R, capital R, on both the numerator and denominator. So we have a z over capital R, and then over square root of c over R quantity square plus 1. Okay, here R is infinity. R is infinity, which means that R is much, much larger than z. Or z over R tends to 0. So this term tends to 0. This term also tends to 0. So this whole term will tend to 0. So finally, if we assume that the disk is infinitely large or infinite disk, this is 0. So this is 1 minus 0, which is 1. So finally, it becomes a very, very elegant expression. E equals sigma over 2 epsilon naught, which is a constant. This is the surface charge density. This is the permittivity constant. So this whole thing is a constant. So which means that if we have an infinitely large disk, it will generate the E field, which is uniform in the space. This is what we have got at the very, very beginning. Here. So if we have a very, very large charge plate, if it is very large circle, which is very large rectangle, so nothing different. So if it's a very, very large charge disk, it will generate uniform E field over the space. Okay. So, okay, so we pretty much finished this part.